Hello, Geography 101 students. I know it's been a bit of a difficult week here for everybody, so hang in there. One of the things I want to do is go over a quick review of Chapter 3 because we didn't get much of a chance to cover that in its entirety, and things might have been a little rushed there. So let's go over this together. This will help you for your upcoming quiz and, of course, your upcoming exam next Monday. So here we go, Chapter 3, Temperature and Insolation. So basically, we're going to be dealing with temperature and then insolation. So temperature is a measure of the heat energy that's stored in an object or a substance, measured by a device called a thermometer. Now, heat itself is related to, or a form of energy related to how molecules will vibrate and also how they collide with one another. So the more energy or the more heat a substance has, or maybe water or air, the more heat energy they have, those molecules will vibrate more, collide more. And if they vibrate more and collide more, they're going to want to spread out because they keep hitting each other and basically spreading out, decreasing their density. So that's kind of the basics of some physics around this of how air behaves once it has absorbed some. Okay, bear with me because as I say, I'm just doing this for the first time for an online environment, so I'm going to make a few mistakes here. And you're probably doing the same thing as you're learning all these different programs. So again, degrees Fahrenheit converting to degrees Celsius. You take your degrees Fahrenheit number and you subtract 32. Do that first. So if it was 68 degrees Fahrenheit this afternoon, what is that in degrees Celsius? You take the 68 degrees Fahrenheit, subtract 32. That comes out to 36. We have to do that part first, and then divide by 1.8. So 36 divided by 1.8 would give us 20 degrees Celsius. If we know our degrees Celsius and we have to convert to degrees Fahrenheit, that's pretty much the opposite of what we just did. You take the degrees Celsius multiplied by 1.8, and then you add 32. So if we had maybe a temperature of 100 degrees Celsius, we want to find out what that is in degrees Fahrenheit. So you take your 100 degrees Celsius times 1.8. That gives us 180. Add 32 for a grand total of 212 degrees Fahrenheit. So water will boil at 100 degrees Celsius or 212 degrees Fahrenheit. The next part of the chapter deals with insolation. Insolation is a single word made up of parts of three words. So incoming solar radiation. Insolation is basically what your teacher would have called sunbeams in grade school or sunlight. So basically, incoming means it's coming down to the earth, solar coming from the sun, and what is it? Is radiation. What kind of radiation? Well, it's waves, or mostly waves, of electromagnetic waves coming down from the sun towards the earth. That's going to travel about 93 million miles on average and take about 8.3 minutes to get to us in the form of these various waves, all coming at the speed of light. So basically, we can look at each wave all traveling at the same speed, but these waves have a different distance between each crest, and we refer to that distance as the wave length. So we have long wavelength, we have medium wavelength, and we have very short wavelength radiation coming down from the sun to the earth, traveling at the speed of light, about 93 million miles. That's going to take about 8.3 minutes to get to us from the sun. Now, at the top of the atmosphere, up here at the top of the atmosphere, every place pointing towards the sun will get the same amount of energy, about 2 calories for every square centimeter every single minute. So it doesn't change. And we call that, because it doesn't change, we call that a constant. And because it's coming from the sun, we call it the solar constant. So the solar constant is 2 calories of energy per square centimeter per minute received at the top of the atmosphere. Now, the energy still has to make its way from the top of the atmosphere through the atmosphere, and we're going to be looking at that in just a couple of minutes. First of all, a little bit more about those waves. Again, we had, as was discussed, we had very short wavelengths and we had very long wavelengths. So cosmic rays, gamma rays, X-rays, ultraviolet or UV rays, visible light, infrared, microwaves, TV and radio waves. This goes from short, very short wavelengths all the way through very long wavelengths. So remember, that difference was the distance between the crest of each wave. Now, we can see in this visible portion of the spectrum right here, we've got a little bit of a rainbow effect because that is representative of the different colors here. And the different colors that we can see are just purely based on how our eyes and brain perceive these different wavelengths of energy coming from the sun. For instance, if that wavelength was 0.7 micrometers, we would perceive that as red light. And if we saw 0.4 micrometers, we would see a violet color because that's violet light. If we had a wave that was shorter than 0.4 micrometers, maybe somewhere out here, we would not be able to see it. That is shorter than violet. It is beyond violet. It is ultraviolet. So basically, in the ultraviolet portion of the spectrum. Whereas if we go longer than red, we would be in the infrared portion of the spectrum. Outside of the red, we can't see it. Doesn't mean it's not there, we just can't see it, but we can certainly feel it in the form of infrared. So if you went to the beach on an August afternoon and you're looking up 1 p.m., 2 p.m., looking up at the sun, you see the sun, you would basically be seeing the visible portion of the spectrum. If you could feel the heat of the rays of the sun, they're warming your body up, that would be the infrared portion you can probably feel there. And if you were there for, let's say, 4 hours and you didn't put any sunscreen on, you go home, take a shower, all of a sudden in the evening, you notice that your skin isn't the same color anymore. You kind of look like a lobster. That would be the ultraviolet radiation that would have burned you. So basically, the short wavelengths, and we can count some of the visible light all the way through ultraviolet, X-rays, gamma rays, cosmic waves, those are going to be damaging to your skin, especially the ultraviolet through the cosmic rays. In fact, these will even damage and disrupt the cells of your body, so you can get skin cancer and cataracts and stuff like that from those. On the other hand, the longer wavelengths, infrared, microwaves, TV waves, radio waves, etc., those will not damage you unless they are amplified in some manner. That's how we can use microwaves to heat up food. It's a little bit absorbing of high energy because the frequency is, or the amplitude is quite large there, but the wavelength is still within microwaves. Okay. Let's move on. So most of the energy coming from the sun is in the short wavelength portion of the spectrum. So the sun basically is going to send towards the Earth, and in fact, it's going to send in all directions, largely short wavelengths, because the sun, being a star, is very, very hot, over 11,000 degrees Fahrenheit, and way beyond that. It enables those molecules to vibrate in such a way that they will send out very, very short wavelength radiation out in all directions. So from the sun, the energy goes out in all directions. We are 93 million miles away. We only intercept about a half of a billionth of that energy. And we're going to use that to heat up and do all of our weather patterns, storms, evaporation, growing of crops, etc. All the energy we need on this planet is basically going to be coming from the sun, or let's say 99.999% of that energy that we need is coming from the sun. And again, most of it in the shorter portion of the spectrum. Now the Earth, of course, we're only getting a half of a billionth of that energy. We're not going to be able to heat up to anywhere near the temperature of the sun, even if we absorbed everything we possibly could. So I know this is a little bit hard to see because my big head is covering it over here, but basically what this is showing is that the sun is hot, okay, no duh, and the Earth is way cooler, so 11,000 degrees Fahrenheit plus and about 60 degrees Fahrenheit on average. And hotter objects like the sun can emit short wavelengths, but the Earth, being way cooler, can only emit or give off, radiate the longer wavelength, or those in the infrared or heat portion of the thermal infrared portion of the spectrum. So what this chart is showing us here, it's hard to see, these are wavelengths getting smaller over here. The peak energy from the sun is in the short wavelength energy portion of the spectrum, and the Earth is going to re-radiate or emit very long wavelengths. So again, that's the relationship between the temperature of a body and what kind of wavelengths it can emit. So the energy is going to come from the sun cross 93 million miles of space at the speed of light, get to the top of our atmosphere, where we get about 2 calories of energy for every square centimeter every single minute. But that energy now has to make its way through our atmosphere, has to get all the way through the atmosphere. And 4 things are going to happen along the way. 2 of them are major because ultimately the energy from the sun will either get reflected or it will get absorbed. And in between, we're going to see a couple little transient processes like scattering and transmission. So let's get into each of those independently. Okay, welcome back. I keep making this mistake by hitting the button that advances a slide instead of the hitting the button that does the highlighter. So my apologies on that. Basically, again, reflection is a bouncing back to space of energy coming from the sun. Lighter colored objects tend to do very well at reflecting. For instance, up in our atmosphere, about 17% of the incoming solar radiation is reflected by clouds. So the energy comes in and hits a cloud, bang, bounces back into space. So again, 17% by clouds. There are other things in the atmosphere, things like light-colored dust particles, light-colored pollen, ice that's not part of a cloud, or ice that is part of a cloud, and we have ash that's light colored. So lighter colored objects in the atmosphere, very fine, they can be suspended for quite some time. The energy from the sun will come and hit those and bounce back to space. And collectively, those will reflect about 8% of the incoming solar radiation. So about 8% for the rest of the atmosphere and 17% from clouds reflecting energy back into space. So if we add those 2 together, the entire atmosphere would reflect about 25% of the incoming solar radiation. Again, 25% reflected by the atmosphere, but predominantly by clouds. Now, some of that energy makes its way down to the surface of the Earth. In fact, just over half of it makes its way to the surface of the Earth and hits some surfaces and bounces back to space. So we have some light-colored objects on the surface of the Earth that bounce that energy or reflect it back to space. And those light-colored objects might be things like light-colored sand, light rocks, maybe even snow, ice, concrete. So things of a lighter color will tend to reflect, but the surface of the Earth is just going to reflect about 6% of the energy back into space. So we have 25% reflection from the atmosphere. We have 6% on the surface of the Earth. So the total amount of energy coming down from the sun that is reflected back into space by the planet is 31%. Again, 25% from the atmosphere, 6% from the surface of the Earth, total of 31%. And we call that the Earth's albedo. So the Earth's albedo, currently 31%, is a percentage of insolation that Earth reflects back to space. Now think about this for a moment, especially in terms of things we talked about in Chapter 2, in terms of climate change. What would happen if we had a large surface of the Earth covered by ice, and we had incoming solar radiation hitting that ice and reflecting that energy back into space? And then, over a period of years, we started to lose some of that ice. So less ice means less reflection. Less reflection means we're absorbing more energy. If we're absorbing more, we are heating up more. If we're heating up more, we get less ice. If we get less ice, we're going to have less reflection. Less reflection, we're going to have more absorption and heat up. And if we heat up, we get less ice. So we get these cycles that develop every now and then where we change the amount of ice and other reflective surfaces on the planet, and those will allow the albedo of the Earth to change over time. So currently the albedo of the Earth is 31%, but it would have been considerably higher than that at the peak of the last ice age. And maybe in the coming years, we're going to see less ice, and therefore the Earth's albedo will decrease, which will further the process of climate change and global warming, because less reflective surfaces, we're going to be heating up. Okay, so the opposite of reflection is absorption. And absorption means that the energy from the sun, the incoming solar radiation, gets captured by things on the Earth's atmosphere and on the Earth's surface. So within the atmosphere, in terms of the absorption, we have things like ozone, and ozone will absorb about 3% of the incoming solar radiation. Clouds, which are good reflectors are somewhat good at absorbing too. So depending on the type of the cloud, the thickness of the cloud, how high the cloud is versus how low it is in the atmosphere, will depend on how good of a reflector or absorber it is, but clouds will basically absorb about 4% of the incoming solar radiation. So 3% from ozone and 4% from clouds, and the rest of the atmosphere, the gases in the atmosphere, the water vapor in the atmosphere, darker dust particles, darker pollen, things of this nature, will absorb about 16%. So in total, we're looking at 3% from ozone, 4% from clouds, 16% for the rest of the atmosphere, the gases, for a total of 23% of the incoming solar radiation is absorbed by the atmosphere. Again, 23%. Now, the best place for absorbing incoming solar radiation is actually the surface of the Earth. Not just the plants, which are very good absorbers. They'll absorb energy and convert that energy into plant food, or basically carbohydrates and proteins and sugars, etc. But the surface of the Earth is going to absorb 46% of the total incoming solar radiation. That's by far the best place to absorb energy. So, dark colored objects, that could be dark sand, dark rocks, that could be ocean water, it could be land surfaces that are dark in color, soil, etc. These are great absorbing surfaces. If we look at non-natural surfaces rather than concrete, which can be a good reflector as well as absorber, but asphalt would be a fantastic absorber of energy. And you think about that. Asphalt in the afternoon, in the summertime, really heats up because it's absorbing that energy all day long. So 46% is absorbed at the surface of the Earth, 23% is absorbed at the within the atmosphere. So a total of 69% of the incoming solar radiation is absorbed by the Earth. We don't give that a special name, but we do keep in mind, if 69% is absorbed by the Earth and 31% was reflected by the Earth, that adds up to 100%. So ultimately, energy gets absorbed or it gets reflected. Let's check that out in this diagram here just to make sure we got our numbers right. Let's work with reflection first. Here's 100% of the insolation coming down from the sun. We have 4% absorbed by clouds. I broke out the ozone. We have 3% absorbed by ozone and 16% by the rest of the atmosphere. But that gives us a total of 23% for the atmosphere. And as far as the energy that makes its way down to the surface, 46% gets absorbed. So our total absorption would be 46 plus 4 plus 19 for a total of 69% of the total 100% insolation is absorbed. So again, 69% of that 100% is absorbed. As far as reflection goes, if you remember, we had 17% reflected by clouds, 8% by the rest of the atmosphere for a total of 25% in the atmosphere, and 6% is actually reflected from the surface of the Earth. And that adds up to a grand total of 8 plus 17 is 25 plus 6, 31%. And that's Earth's albedo, the percentage of insolation reflected by the Earth. Okay, I know it's a lot to cover so far, but bear with me. We're moving along this material quite quickly. You can also follow along on the regular PowerPoint, but you could also take a look at the textbook or your classroom notes. Okay, moving on here. Oh, before I do that, how much of the energy from the sun, that 100%, makes it to the surface of the Earth? A lot of people kind of get confused by this question. So how much of it actually made it to the surface of the Earth? Well, we know it's the 46% that was absorbed plus the 6% that was reflected. So basically 46 plus 6, 52% of the energy made its way to the surface of the Earth. Where is the best place to absorb energy? Surface of the Earth. What happens to the temperature when things absorb energy? They warm up. So the surface of the Earth warms up. Where will it give its energy to? Well, where's the first place it can give its energy to? The atmosphere right above it. So energy absorbed at the surface is going to try and get up into the atmosphere. And we'll learn later on that that's why the atmosphere is warmest here, it's certainly in the troposphere, that lower layer is going to get colder and colder and colder as you go up because you're moving away from the area where most energy gets absorbed. Okay, just a little diagram here, absorption and reflection. There's somebody skiing with a light colored top. That's going to reflect a lot of energy and not heat up as much. Or dark colored ski bib here would warm up quite a bit more. And in that case, if you had snow falling on it, it would melt more frequently on that darker color. Now, one thing you always tell if someone has gone, especially in springtime, if they went skiing, because they're going to come back to school. They've been wearing goggles while they've been skiing, and those goggles will reflect the energy straight from the surface of the or the UV protection of those goggles onto their nose, giving them quite a bit of a sunburn. Plus, the energy from the sun hits the snow, a good reflector, boom, and gives that person a sunburn. Plus, they're usually skiing up in the mountains with less atmosphere above them, and a lot of atmosphere is still below them, so the atmosphere is thinner, and therefore we get less molecules above us to interfere with this incoming solar radiation, so the sun rays are a bit stronger. So you get kind of a triple dose from the sun and from the reflection from the goggles and a reflection from the snow. So you got to put sunscreen on when you go up in those mountains. So I'm having this horrible habit of hitting the wrong button here, but basically scattering those small particles in the atmosphere remove the short wavelengths from the incoming ray of sunlight. So the first to get removed here are the violets and the indigos and the blues. And during the daytime, that means that we've got red, orange, yellow, green, blue, indigo, violet wavelengths all adding up to pure white. Coming through the atmosphere, the violets get removed, the indigos get removed, the blues get removed and bounce around, all around, so that the sky appears to be blue. And what's left to our eye is red, orange, yellow, green, blue, indigo, violet, minus blue, indigo, violet. So we get the color yellow when we look up towards the sun during the daytime. Now in the evening, when the sun has to go through a portion of the atmosphere at a very low angle, we get the light coming in, we get the violets removed, the indigos removed, we get the blues removed, the greens removed, and at the very last minute, the yellows bounce around, and the only thing left to hit our eye when the sun is at the horizon would be those red and orange colors. So we see a red-orange sun surrounded by a yellow sky in the evening, but during the daytime, we get a blue sky surrounded by a yellow sun. Let's look at the next slide here again. So basically, we've got red, orange, yellow, green, blue, indigo, violet coming down from the sun. The shorter wavelengths get removed, and depending on how many particles are in the atmosphere and the angle of the sun will tell us just how many wavelengths get removed. Is it the violets, is it the indigos, the blues, and the greens, or is it the violet, indigos, and blues only? So during the daytime, we still have green, yellow, orange, red adding up to give us a yellow sun, but sorry, that would be in the afternoon, a green, yellow, orange, and red adding up to a yellow sun. But in the evening time, at sunset and sunrise, we only get yellows, oranges, and reds coming through, and we get that yellowy sun and orange, red. Sorry, an orange, red sun and a orangey yellow sky. I might have to put up another diagram about that. Let's see if we have time. Okay, transmission is the last of those processes, and we've talked about this before, that there are gases in the atmosphere that allow the short wavelengths from the sun to pass on through, to get transmitted through the atmosphere all the way to the surface of the Earth. And then, afterwards, the Earth is going to absorb the energy and try to give long wavelengths back into space. And those same gases won't let that energy out, so the energy gets temporarily trapped in the lower atmosphere. So what are those gases? We call them the greenhouse gases. And yes, you're right. That's carbon dioxide, water vapor, methane, oxides of nitrogen, CFCs, ozone, etc. So short wavelengths coming in. They get transmitted through the atmosphere, no problem. Long wavelengths can't go out so easily. So those gases are going to temporarily trap that energy. Now, you might look at this diagram and say, so where's most of that energy going to be absorbed anyway? And it is correct to think most energy is going to be absorbed at the surface near the equator, because this is the area where we're closest to the direct ray of the sun all the time. So this area near the equator here is going to absorb a tremendous amount of energy every single year, probably more than what it needs to maintain its temperature. So this is an area of energy surplus. Now, if I look towards the poles, because of the angle of the sun coming in, these areas up here, they don't get enough energy. They should be cooling down, as should these areas in the south polar region. So these areas are those of energy deficit. So we have areas of energy surplus and areas of energy deficit. So where do those lie? Well, basically, if you are 28 degrees north all the way to the North Pole and 33 degrees south all the way to the South Pole, you'd be in energy deficit area. But if you're from 28 degrees north to the equator all the way down to 33 degrees south, you would be in energy surplus area. Why is that so? And why is it not so even? We could round these off, and we often do, and say that we have an energy surplus zone from about 30 degrees north to 30 degrees south. So again, from about 30 degrees north to about 30 degrees south, that would be an energy surplus area. But in actual fact, the energy surplus doesn't extend quite so far to the north. It extends a little bit further to the south. Well, one reason for that is that the southern hemisphere has a lot more water exposure at these latitudes, and water can absorb energy very, very well. It doesn't mean it's going to heat up completely. It's going to basically absorb that energy without increasing its temperature so much. But it is going to absorb and keep that energy. The northern hemisphere has a lot more land surface and doesn't behave the same way. Also, if you think about it, we are closest to the sun, remember perihelion, and that occurs in January. And for the northern hemisphere, that's during our winter. And think about that for the southern hemisphere. Perihelion on or around January the 3rd would be towards the beginning of summer for the southern hemisphere. So the sun is at a higher angle at that time in the southern hemisphere, and it gives them an opportunity to absorb more energy and become an energy surplus area, even at latitudes like 30 degrees south, whereas 30 degrees north is not really an energy surplus zone. We're going to round this off for most intents and purposes and say about 30 degrees north to about 30 degrees south. Okay. So the energy surplus areas should be warming up, and they are. So between 30 degrees north and 30 degrees south, centered on the equator every year, they are warming up a little bit. This is part of what we call climate change or global warming. Now the areas from 30 degrees north to the North Pole and 30 degrees south to the South Pole should be cooling down. But in fact, they're warming up, and they're warming up faster than the energy surplus zones. And the only way to explain that is that energy from the surplus zones are moving to the energy deficit zones. And how does that occur? Well, we call those energy transfer mechanisms. So let's go through each. We have re-radiation, conduction, convection, adiabatic cooling and warming, latent heat transfer, and oceanic and atmospheric circulation. Let's look at them one by one. So re-radiation means that the Earth absorbs energy from the sun, those short wavelengths. The Earth's surface, remember, Earth's surface absorbs 46% of that energy. It's going to heat up. And now the Earth is going to give off energy, the only energy it can. Well, remember, it can only heat up a little bit. The average temperature of the Earth is about 60 degrees Fahrenheit, not 11,000 degrees. So basically, the Earth can only give off long wavelengths or infrared radiation back into space. An example of that might be found here. Now, this might be a fire, or let's think about a hot asphalt parking lot that's just been out in the sun all day. So basically, if that asphalt parking lot had absorbed heat, or the analogy here being a fire, even at nighttime, you can feel heat emanating from this fire right here. Well, you could feel the heat emanating from a hot asphalt parking lot all the way through the evening and late night hours, long after the sun has set, because it absorbs energy and then radiates that energy back into space in the form of long wavelengths. Again, you don't have to put your hands into that fire to feel the heat. That heat is being radiated towards you. The same like you wouldn't have to put your hands onto a hot asphalt parking lot to feel the heat. You could put your hands right above that parking lot and feel the heat that way through that re-radiation of long wavelengths. The second energy transfer mechanism is called conduction, and conduction refers to the transfer of energy from a hotter object to a cooler object in contact. They have to be touching. So in this case, what happens if you touch that hot asphalt parking lot? If your hand actually touched that asphalt, well, your hand would heat up. There would be transfer of energy from the asphalt into your hand because those two objects are in contact. Now, if molecules in the atmosphere did the same thing, they touch the hot asphalt parking lot, those molecules of air would pick up some of that heat and they would actually vibrate more, collide more. They'd probably move upwards and then do the same thing, bumping into other molecules and having that direct energy transfer every time they collided with another molecule. So the direct contact exchange of heat, that's referred to as conduction. Another example of that would be sticking an iron rod into the fire and basically leave it there a long time, and the molecules are going to get energy transferred along the length of that iron rod. And if you touched, after 20 minutes, you touch the end of that rod, you would burn your hand over here because those molecules are being transferred in that heat along. All right, convection is defined as basically the vertical and horizontal movement of air. So in our context here, transfer by convection or heat transfer means that heat is transferred as air is moved both horizontally and vertically. So basically, if you have some air over here, it's being warmed up. Okay, same hot asphalt parking lot, heats the air above it. That air wants to go up, and as it goes up, it's going to share energy with those molecules around it through conduction. But that same air, as it goes up, is losing that heat. So it wants to come back down, but it can't come back down because the air is still coming up from below. So it's going to find a pathway to fall down, come back towards the surface, pick up some more heat from the parking lot, woo, up it goes again. So basically we have a sharing of this heat, a transfer of the heat in the lower atmosphere, absorbing energy here, but moving it in that entire maybe 2,000, 20,000, 50,000 feet of lower atmosphere, depending on many factors here. So there's convection again. I think you can see the same thing, just a blown up diagram of that. Now this one is involving a little bit of physics. Adiabatic cooling and adiabatic warming. Basically, adiabatic means this involves air that is rising or sinking. And think about it. As air rises, it's going to go into an atmosphere that gets thinner and thinner and thinner or less dense. And if air was to sink into our atmosphere, it's going to be surrounded by molecules pushing in from all sides with a lot more dense. So what this means is that air that will rise will have its molecules spread out because of the lower density. And if those molecules spread out, they're going to collide less. They're going to vibrate less, and therefore they're going to cool down. So every time air rises, the air cools. Conversely, air that sinks in the atmosphere, those molecules are going to get crushed and crushed and crushed, tighter and tighter and tighter together. And as those molecules get tighter together because of the outside pressure, they're going to get more collisions and more vibrations. They're going to heat up. So as a general rule, what we see is air that rises and expands is going to cool. So rising air will always cool. And that type of cooling is called adiabatic cooling. And molecules in the atmosphere that sink are always going to get crushed together and they're going to warm up. So that's called adiabatic warming. It's just a physics process that's related to how the temperature is dependent on the pressure and, of course, the volume of air being constant in that case. Here we go with latent heat. This one's a funny one. Latent heat means hidden heat. Well, heat can take various forms. It can hide in various ways. And one of the ways is that molecules of, let's say, water in this case, because this is going to involve the molecule water, the molecules can be in three different forms on this planet, or three different phases. So we use the word phase for water to represent, is it in a solid phase, which we call ice? Is it in a liquid phase, which we call water? Or is it in a vapor phase, which we call water vapor, as a gaseous phase? So water can exist as ice in its lowest energy phase, as water or liquid water in its middle energy phase, and it can exist as water vapor in its highest energy phase. And then in this one, the molecules are vibrating and colliding like crazy because they've absorbed a tremendous amount of energy from somewhere. Well, where does that energy come from? Ultimately, the sun. So the sun can take water, add energy to it, and change the phase of water. Look at this. What this is showing is if we add energy in this direction, so more energy going in this direction, we can take ice and we can melt it into water. We can add even more energy and we can evaporate that water into water vapor, okay, the highest energy phase. Conversely, if we had, as we go on, ice, add energy, go to water. Well, where does the energy go? It's into water. Water, add some more energy and evaporate it into water vapor. Where's the energy go? Well, it's into water vapor. It's hidden in the form of the water. Take the water vapor, and now we're going to release energy into the environment. Take the water to the lower energy phase, and it becomes water. So water vapor becoming water. Where did the energy go? Into the environment. Water, take energy out of it even more by freezing into ice. The energy that used to be in the water as a liquid form, which is now ice, has been released into the environment. Now, it sounds like, well, it is. It's physics, but basically, let's look at how it plays out in reality here. Back again. So basically, at the surface of the Earth, we've got a back and forth, the surface of the water, back and forth of water in a liquid form jumping into a gaseous form as water vapor, and water vapor jumping back down in energy phase from that vapor into a liquid. So they go back and forth, back and forth, back and forth. If we added an awful lot of energy from the sun, we could evaporate at that surface a lot more of the liquid molecules and turn them into a water vapor. You cannot see the water vapor, but as this process goes on, we've got liquid water evaporating into water vapor, and that requires a tremendous amount of energy, and the energy goes into those water vapor molecules. Now, you cannot see the process because water vapor is invisible. You cannot see water vapor, but water vapor being heated up here would tend to rise. As it rises, it's going to cool. That's adiabatic cooling. Continue up, it's going rising up, cooling, 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 then boom, right here at the base of this cloud, what's going to happen is water vapor has now gotten so cool it can't exist as a water vapor anymore. It's got to exist now as a liquid droplet. So we get condensation occurring here. And as those water vapor molecules condense into liquid droplets of water, tiny droplets of water, they're going to release energy into the environment, in this case into that cloud, making the cloud warmer than the air around it, which helps accentuate the lifting process. Because remember, these molecules are rising. So you got little droplets of water right here, and they've just taken energy that was absorbed at the surface, so solar energy absorbed to the surface, and now depositing that energy into that cloud through the process of evaporation and then condensation. So those droplets, by the way, they're heavier than air. They should fall back down, but they don't. And that's what you see in the cloud. You see those droplets of water that have just condensed out. Why don't they fall down? Well, because the air is moving up. So suspending those droplets there until those droplets get big enough to fall out, which doesn't always happen, but in later chapters we'll explain that process a bit more. So as you can see, we got a cloud. The clouds stay put? No, they can move anywhere. So clouds basically going to take that energy with them and move in any direction. So we get an energy transfer mechanism associated with latent heat transfer. And that also is linked to one of our other processes coming up. Atmospheric and oceanic circulation. So basically, we just showed a little bit about latent heat transferring energy into the atmosphere, but now those clouds can move and they can take that energy, pretty much energy from east coast of the US, over towards Europe. The same thing with ocean currents. You notice in the North Atlantic, the ocean current is clockwise. South Atlantic, counterclockwise. We'll talk about that in chapter 4. Result of something called the Coriolis force or Coriolis effect. But basically, our oceans can absorb tremendous amounts of heat here in the tropical oceans. And because of these ocean currents, we can take heat absorbed all the way over here in the tropical Atlantic, move it along the coast of Florida, where it's hot and sticky, the Carolinas, up along the east coast of the US, out by New York, into Canada, out into the ocean, and bring us some of that same energy all the way to Ireland, Norway, even to Russia, making these areas here warmer than what they should be, because energy absorbed at the equator has been taken all the way towards, well, towards the pole, so into the Arctic over here. Again, making these areas over here warm, way warmer than what they should be without that ocean current. So ocean currents and atmospheric currents can transport energy absorbed in one place to another place quite easily. Okay, so we covered the 6 energy transfer mechanisms, and now we're going to talk about the 7 controls on temperature and wrap this chapter up. I know it's quite a pace, but they should help you in many ways, kind of refresh your mind about what we talked about in class, or maybe would have talked about in class had we had one. So basically, 7 controls on temperature. These by now should be quite familiar. You think about it, we've looked about these in chapter 2, and we're now applying them, and we'll continue to apply them to other chapters. So what makes a temperature different in one place to another place? Well, there's some pretty obvious ones, and there are some pretty not so obvious ones, and then we'll go into depth on the effects in one of these in particular. So basically, latitude, elevation, distance from a large water body, general circulation of the atmosphere, general circulation of the oceans, topographic or mountain barriers, and finally storm tracks. So let's explore these one by one. Latitude. Well, because of direct ray of the sun, the average position is by the equator. In general, we'll say that because of absorption, the equatorial regions are warm, when that is true, and the polar zones are pretty cold. So if I said to you, can you tell me a place right now that is definitely warm, and you chose a place near the equator, you'd be correct. If I said, tell me a place that's almost definitely pretty cold, one place you might say would be like northern Alaska, or maybe you'd say the North Pole even, and you'd be correct in that case too. Another factor is elevation. The further a place sticks up into the troposphere, the colder it's going to be. So we can tell in this diagram, high elevation, cold, and lower elevation, warm, because their atmosphere warms the lower you get into it in general. Now this one, distance from a large water body. This is basically a reflection of how, or temperature differences can be explained by how far you are away from a coastline, because coastlines of large water bodies have moisture in the air, and moisture in the air means that temperatures can't get too wacky. So if you're near a coastline, you're going to have summers that are not so hot, and you're going to have winters that are not so cold compared to places at the same latitude that are further inland. And if you are inland, you can get temperatures in the summertime that are pretty dang hot and winters that are pretty dang cold compared to places at a coastline. Now, one of the ways that we measure this or show this is through something called the annual temperature range. Remember, this word range means difference. And annual, yearly, temperature difference. This means, or annual temperature range, the difference between the average temperature of the warmest month and the average temperature of the coolest month. So you take the average temperature of the warmest month, you subtract the average temperature of the coolest month, and that will give you the annual temperature range for any place on the planet. And what we notice is that places along the coastlines have low annual temperature ranges compared to places that are inland. So if we draw a line along the same line of latitude, we can see that along maybe our coast, we're looking at close to 30 degrees Fahrenheit. That's even a bit high, to tell you the truth. And then we go inland and we're looking at something about 50 degrees Fahrenheit. Now look at Europe as you go into, let's say, Great Britain, somewhere around there. We're looking at about 20 degrees Fahrenheit annual temperature range. But you come inland into Siberia, and we're looking at 90 to 100 degrees Fahrenheit. That means that these places in Siberia would see about 100 degree Fahrenheit difference between their summer and wintertime temperatures. How can that be explained? That air here must be pretty dry, whereas at the coastlines, the air is pretty moist because, again, moisture in the air has a moderating effect on temperatures. So annual temperature range is ATR, abbreviated annual temperature range, the difference between the temperature of the warmest month and the temperature of the coolest month. And again, they're going to tend to be low on coastal places, also going to tend to be low for equatorial places, and higher, much higher, for those places closer towards the poles. So annual temperature range. It's also related to daily temperature range. So daily temperature range is a difference between the warmest temperature of the day, typically found between about 2 and 4 p.m., so middle of the afternoon, warmest temperatures, and the coolest temperature of the day. And the coldest temperature for the day, or coolest temperature for the day, is normally found right around sunrise. Because you think about it, what's going to happen is the sun is going to be up. It's going to warm things up to about 2 to 4 p.m. The air is going to mix because of convection, and we kind of get our maximum temperatures in. And then the sun is slowly going to go down, and temperatures will follow going down also. The sun goes behind the horizon. Now we don't get any sun, so the temperatures get colder throughout midnight, 1 a.m., 2 a.m., 4 a.m., until that sun comes up. And when the sun comes up, there's our new source of energy. Now temperatures will start to rise again. And by the way, when the sun comes up, we call that sunrise. So that's our coolest time of the day. Now the difference between the coolest time of the day and the warmest time of the day, or I should say the difference between the warmest time of the day and the coolest time of the day, through subtraction, is referred to as the daily temperature range, and it also tends to be low for coastlines and high for inland areas or continental areas, low for tropical areas, and higher for higher latitude places. So annual temperature range, daily temperature range, they both relate to how much moisture is in the air. One thing I didn't mention, by the way, for annual temperature range, typically the warmest month would be, for most, but not all places, but for most places, would be about 2 months after the summer solstice. And the coolest month would be a month or two after the winter solstice. So for us here in LA, our warmest month is probably going to be around August, 2 months after our June solstice. And our coolest month is going to be around February, because that's about 2 months after our December solstice. So we'd look at those temperatures for those months, subtract them to find out our own annual temperature range. Now for daily temperature range, of course, we look at the early morning temperatures, we look at the afternoon temperatures. The difference between them will give us our daily temperature range. So why is it that coastlines and moist places have this moderating effect in terms of temperatures, where it doesn't get too hot, doesn't get too cold? And a lot of it has to do with the fact that if you've got moisture in the air, it's going to act as if we had a water surface, basically. Now, water itself takes a whole lot of energy in order to change the temperature. Also, water doesn't just get too hot by absorbing just molecules at the surface. If it absorbed too much heat, it could evaporate. If we had heat absorbed on the surface over here, the surface will kind of convect and mix up from the lower layers. Whereas land over here, first of all, it takes about a fifth of the amount of energy on land to change the temperature of, let's say, soil or rock than it does to change the temperature of, or increase the temperature of, water. Also, at the surface, it's going to heat an awful lot of, or absorb an awful lot of incoming solar radiation and heat up. This can't convect. We don't see like the soil convecting here because of solar energy being absorbed. So it can't mix. It heats up more naturally anyway, and it's a very thin layer that does heat up. And think about that when you go to the beach. That top layer of sand can really get hot but if you get caught in the middle of a really hot sand area, you can just dig your feet down about an inch or so, and that's nice cool sand below there. So moisture from here gets evaporated into the air, and that's going to help to reflect some of that energy back into space and not let the coastal areas heat up quite as much as the inland areas where there's no moisture in the air. So examples here, I mean, Dallas is a little bit further away from the coast than is San Diego, especially the marina area of San Diego. So San Diego's temperatures in the middle of summer are not going to get quite as hot as what Dallas's temperatures would be being further from the coast. Conversely, because that moisture is in the air in San Diego's winter temperatures don't get quite so cold. Dallas being further away from a coastline with drier air is going to see colder winter temperatures and warmer summer temperatures. San Diego, warmer winter temperatures, cooler summer temperatures. Can you see that San Diego's annual temperature range, the difference between the warmest and coolest months, would be quite low compared to Dallas's annual temperature range, which would be represented by the length of whatever this line would be here. Much larger difference between the summer month temperatures and the winter month temperatures. Okay, in fact, it even gives you the numbers right here. The annual temperature range for Dallas would be annual temperature. Oh, sorry, that's not giving you the range there. That's average annual temperature. It's the range we're looking at, which would be, or need to look at, which would be the difference between these. Okay. Again, distance from a large water body, and what will you see? We're going to see high annual temperature ranges inland places and very low along coastal places. I hope that makes sense by now. So for the general circulation of the atmosphere, along the equator, it's pretty warm. So this area here is pretty warm. And warm air always wants to rise. So I'm going to show you on the side here, the air is rising. As the air rises, it's going to cool adiabatically. It's going to condense, and it's going to give us clouds. So at the equator, we get lots of clouds and lots of rain. And that rain is going to fall back to the surface, and it's going to allow tropical rainforests to grow because we get this constant moisture at the equator with plenty of sunlight, very conducive to tropical rainforest formation. So if you went to the equator or near the equator, you're going to find it to be pretty warm conditions and also pretty moist conditions. That same air that was rising is going to hit the top of the troposphere, and it's going to split, and some of that air is going to move towards 30 degrees north and sink down, and some of it will move to 30 degrees south and sink down. So at 30 degrees north, right here, and 30 degrees south, right here, we have sinking air. And sinking air can't form clouds. So we don't get clouds in the sky. We got pretty sunny skies, pretty sunny conditions. So sun that's not that far from being overhead, plus no rain, that's perfect for deserts. So we get deserts pretty much around 30 degrees north of the equator, and we get deserts at 30 degrees south of the equator. Now, because of the cloud cover in summertime, which is almost year-round in the equator, so during the high sun seasons, we're going to see that at the equator, things are not hot. They're just very, very, very warm and moist. That moisture in the air doesn't let it get too hot, for one thing. But also, we're going to see here that the cloud cover is a good reflector of solar energy. So it doesn't allow so much to reach the surface. So we get very warm conditions. At 30 degrees north and at 30 degrees south, because of the sinking air, we got lots of sunshine. We got dry, hot conditions. This can get those summertime temperatures way above 100, 110, 120, 130 degrees Fahrenheit. The same in the southern hemisphere. So we can get really hot summers here, really warm summers here, and it gets then progressively milder and cooler as you go during summertime towards the poles. So we showed a diagram earlier looking at latitude that showed this to be warm and the poles to be cold. As a matter of fact, we would find, especially in summertime or summer temperatures, would be very warm here at the equator, really hot around 30 degrees north, and then progressively cooler until you get to the cold poles. So again, very warm, then hot, and then it starts to cool off. And part of the reason for this is this general circulation of the atmosphere, and that is clearly affecting temperatures in this example. Again, the oceans circulate, northern hemisphere, they circulate clockwise, and that's going to bring energy absorbed in the, let's see, in this case, the tropical Pacific, and it's going to move that energy along the coast or the east coast of Asia and up towards Alaska. And then that is going to bring cold water down, warm water up, etc. Well, those warm and cold currents are going to affect the temperatures too. So along the east coast of Asia, let's say the Philippines, Japan, parts of China, Hong Kong, etc., these are going to have warm, in fact, they're going to have very warm, humid summers, as are places like the Carolinas and Florida, because the Atlantic has the exact same type of pattern. Conversely, where we get the cold ocean currents coming down the west coast of the US, we're going to get much more stable air, a lot less in terms of rainfall, but also we're going to get very dry conditions as we get down towards about, let's say, 38 to 30 degrees latitude along these coastlines here. So here we can get clear conditions and therefore quite hot summers. So the general circulation of the oceans can impact the temperatures, and as mentioned a little bit earlier, warm ocean water from the tropics, releasing that energy all the way up in Alaska, is going to make Alaska, especially the coast of Alaska over here, warmer than what it really should be. So these ocean currents really can affect our temperatures in many ways. Topographic barriers. I know it's a big word, topographic. Basically think of mountain barriers, so mountains. And what this means is that air that comes up and over a mountain is going to act very differently on both sides. As air comes up a mountain, it's going to basically cool, maybe even release its moisture in the form of clouds, and then sink down the other side of a mountain. And as the air sinks, it will warm up pretty rapidly. So we could get air coming up and giving cloud cover in very moist conditions on one side of a mountain and very dry, hot conditions, especially during summer, on the other side. So if we look at the big island of Hawaii, if we look at the east coast, we have wetter, cooler summers, the Hilo, and look, 150 inches of annual rainfall, and that cloud cover is even going to affect summertime temperatures out here. And as that same air sinks down, goes up and then down or lower in elevation on the west side of the island, that air is going to dry out, clearer skies, and we're going to get, I mean, look at this, 9 inches annual rainfall here, so a lot drier conditions, and even in the summer here, quite a bit hotter on the west side of the big island of Hawaii than it is compared to the east. And lastly, storm tracks. Basically, storms, not all storms, but especially like mid-latitude storms, they have defined paths, or they have ways that they typically move, or directions they typically move, where they come from or where they go to. So for instance, in this diagram here, we see a storm coming in, hitting Ireland and England. Is basically covering those right now. And that storm track for those types of storms, those mid-latitude wave cyclones that hit in the wintertime, we just call them winter storms, they basically come in this direction and off they go, off to the northeast. So they will nail places like Scotland and Ireland, and they'll basically next come into France and then head up towards, in this case, towards Russia. Now, Scotland gets nailed. England gets nailed. Come down to southern England, less rainfall. Into France, less rainfall. You get into Spain and Portugal, even less so. So basically, lots of rainfall, a little bit less, 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 etc. So storm tracks are going to, in this case, affect the moisture, because the storm is certainly bringing moisture. But cloud cover is also going to act to reflect solar energy. And the nature of this storm is such that cold air is moving in to warmer air. So these areas are going to get quite a bit of cold temperatures coming in on the back end of that storm. And as you move further south, a little bit not as cold, not as cold, not as cold, not as cold, not as cold. So if you're in the storm track, you can be impacted by those storms, their moisture and their temperature impacts, a lot more than if you're towards the tip of, or maybe even completely out of the way of these storm tracks. So storm tracks are one of the influences on temperature, just like they are on moisture. And that is the last of these slides. I think that would pretty much wrap up a quick review, admittedly, of this chapter. It looks like it's been about an hour. We would normally take 3 hours or more to cover this chapter. So please review this. We're going to follow up with some questions.